All right, so what we're going to do today is we're going to talk about exceptions to the Kelter strategy, and essentially the method is going to tell us when we need to have a different number of electrons around the middle. Now, typically we want to have either an octet or a duet around the center, but there are times when we're going to have a different number. Now, the two options we have are either going to be having more than an octet around the central atom, and or having between 2 and 8, which really means if you do between 2 and 8, 4 or 6. Now, when can that happen? Well, if you take a look at the periodic table, if you're in the third row or below, you can actually have more than an octet. Now, you prefer to have just 8, but you could very easily have 10 or 12. But I want you to take a look where that encompasses. That's the entirety of this periodic table going down is essentially potentially going to have more than an octet. Now, if you take a look at the exceptions where the electrons are actually, we actually have between 2 and 8, there's only two atoms on the periodic table, boron and beryllium, that can have either 4 or 8. So whenever we're dealing with boron or beryllium, I'm going to circle these right here, because these ones right here, they're almost always going to be exceptions and you need to be aware of them. So the best way to try and work through these is by doing a problem. And I want you to, if you could, I put online, I put the an exceptions version to follow along with the notes, but this is the original version of notes of how we do Lewis structures. And what I'm going to do is I'm going to make a couple points here. Right here at number 3, we're going to do an add-on that tells us what to do when we have an exception. And then at the very bottom with number 7, we're going to do something different. So let's start off with a problem like this. Let's go with BRF3. Now, I'm going to do the steps like we normally would in a problem. And don't we normally go, hey, valence, and we add up all the valence electrons to each other. And if we take a look here, bromine has 7, and then each of the 3 fluorines have 7, so we're going to 3 times 7, and altogether, wouldn't that be 28? I'm running out of space here. That's 28. Now, happy, there are 4 atoms right here. Each of these 4 atoms wants to have 8, so that'd be 4 times 8, and that's 32. And if we do the math here for the number of bonds, which is so that's the happy minus the valence divided by 2. That's 32, subtract 28, divided by 2. If you do the math on that, the number of bonds we're supposed to have is going to be equal to 2. Now, here's the problem. We have 3 things to attach around this bromine. So the way we're going to do this is we're typically going to just put our Br in the middle, and what we're going to do is we're going to attach all of the fluorines on the outside. Now, I want to make a big deal about this because see how this method here tells us that we need just 2 bonds? That is a lie. This atom, there's no way to put together 3 things around the center with just 2 bonds. But the fact that the method is telling us that we need less than we actually do, that means that we are dealing with an exception. So I actually did this in your notes. And if you take a look, it says the method ever lies to you. This is this paragraph down below here. If the method ever lies to you and tells you they need less bonds than you actually do, it means you're dealing with one of the 2 types of exceptions. So what we're going to do then, though, is just go through the rest of the steps as normal. And at the end, we're going to add whatever extra electrons that we're missing around the center. So I'm going to go back up to here. And so what I'm going to do is I'm going to go like I normally would. Since I need to attach all these to the middle, I'm just going to go one line to each of these. Now you may be saying, wait a second, that's not the number of that's the number of bonds that the method said. Correct. The method lied to us and said we only need 2, when we clearly need more than 2. We actually need 3. Then we're going to go ahead and do we just did the skeletal structure. Now we're going to complete the octets around here. So remember, every bond counts as 2 that are being shared. So don't we have 2, 4, 6 around this bromine? Well, let's make an octet. So we're going to put 2 more dots right here. And then each of these fluorines, they have 1 bond attached. And each bond counts as 2 electrons around them. So we have to draw an additional 6 around each one. Same thing over here. Now what we've just done is we made every single atom in this happy. So normally we'd be like high-fiving and everything would be all good. However, if you take a look over here on this far side, the most important piece of information is this 28 over here. Because when we get done, it is really, really important. I'll jump over to here. When we're at step 7, there's a slightly different thing. You count all the electrons in the structure and you make sure that you have the same number as the valence electrons you had in step 1. And once you get done, if the valence electrons you need more of them, you're going to put them around the center, which basically, if we go back to this problem, we have 28 to start with. If we count right here, it's 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24, 26. We only have 26 electrons in this structure. We're supposed to have 28. That's problematic because we can't just lose 2 electrons. So if you go down to step 6 in the notes that I've given you, the exception notes, it says when you don't have enough electrons, you put the extra electrons that you're missing around the center. So see how we have 26, but we really need 28? That means we're going to have to put 2 more electrons around the center. And so it does not matter where you put them, but you're going to put them as a pair. I'm going to put these 2 electrons right here. And what that means now is that this atom in the middle has 2, 4, 6, 8, 10. Now, again, that would normally be really huge cause for alarm, but is bromine in the 3rd row or below? Well, let's take a look where bromine is. Bromine's right here. So it's in the 3rd row or below, which means that any element in the 3rd periodic row can actually have more than an octet. Now, does it prefer to have an octet? Absolutely. But could it take 10 electrons around it? Yep. And the only way we know that it can is by the fact that this method lied to us. So let's try a different example. So let's go with boron, because good old boron, right? We're going to do BH3. And I'm going to do the valence, happy, and number of bonds really quickly here. So if you take a look at boron, boron has, if you look on the periodic table, again, I'm getting all these numbers by looking at the periodic table. In the periodic table, if you take a look at boron, isn't it in the 3rd row? 1, 2, 3. So that's why when we're dealing with boron, we know that boron has 3 electrons, and we know that there are 3 hydrogens. Each of these 3 hydrogens, they want 1. That's how we get 6 for our total number of valence electrons. Now, in order to deal with happy, one of the things that you need to be aware of is that when we're counting up happy, boron is part of the first 5 on the periodic table. So that means it only wants 2 to be happy, right? And hydrogen as well, it's part of the first 5, and it wants to have 2 to be happy. So essentially, do you see how we have 1, 2, 3, 4? We have 4 atoms, and all 4 of those atoms are part of the first 5. So they all want to have 2 to be happy, which means that there are 8 happy electrons. Now, when we do the bonds, what we're going to do is we're going to take our 8, subtract 6 divided by 2. Again, this is our trick, and it's going to tell us we need 1 bond. Now, let's just pause for a moment. I'm going to skeletally draw this out. It's telling us that we need to attach all 3 of these things around the center with 1 bond. To that I say, good sir, you are a liar. And liars tell us that we actually have an exception. Now, we are okay with this being an exception because isn't boron one of the ones that can actually have either 4 or 6 and be happy? So what we're going to do is we're just going to go on our merry way, even though the method has said that this is only needs 1 bond. We know it's a lie. So what we're going to do is we're just going to attach everything to the middle because we have to. 1, 2, 3, right? And then we're going to go around each of these atoms and make sure that they have a full outer shell. Remember, each of these atoms right here, they want 2 to be happy. Each bond counts as 2 electrons that are being shared. So you see how this hydrogen right here has 2 because it's attached with 1 bond. This one has 2 because it's attached with 1 bond. This one has 2 because it's attached with 1 bond. And we also know that boron wants to have 2. It wants 2 electrons. But if we count up around it, with each bond, doesn't it have 2, 4, 6? Which is problematic because we know it only wants to have 2. But isn't this an exception? And isn't boron one of the ones that we can have that has less than an octet? The answer to both those questions is yes. But then we have to do a check. We have to add up all our valence electrons, and they have to equal the 6 electrons that are up here at the top. So if we do the math here, it's going to be 2, 4, 6. If I have 2, 4, 6, isn't that the number we had up here? So this, I'm going to do a check mark for happiness, this is the correct way to draw the structure. I'm going to do one last one here, and the structure I'm going to do for you here is PI5. Now, I'm doing this, and I'm going to go ahead and do the mathematics on it really quickly, valence, happy, and number of bonds. I do apologize for how quickly I'm doing these, but I do not want to have you watching these forever. If you need to go back, you can go back and look at them. Valence, isn't phosphorus, doesn't it have 5 valence electrons? And each of the iodines has 7, so that's going to be 5 times 7. Not a divided mark. So we have 35 plus 5. Would that not give us 40 electrons? We're going to box this because we know that's going to come back into play later. Then also, if we take a look at this, don't we have 6 atoms? And all 6 of those atoms are not part of the first 5. They only want to have 8 to be happy. So we're going to go 6 times 8 is 48. And if we do the math, 48 subtract 40 divided by 2, that's going to give us 4 bonds. Here's the problem. We have a P in the middle. And the other thing I want to pause for a moment, even though I'm going really quickly. Whenever you have an exception, all of your atoms need to be surrounding the central atom. Well, we have 5 atoms that are surrounding this central atom. So we have to attach them some way. But what does our method tell us that we need? It says that we only need 4 bonds. And that is a lie, which means that this is an exception. Whoa, that just went kind of crazy there, didn't it? I'm going to go back here to where we were. Sorry about that. And what I'm going to do is I'm going to attach all of these with at least 1 bond. Now, normally we'd want to put 1 on each side, but we're going to kind of do like a star shape here. We'll worry about actual shapes when we get when we're dealing with the shapes of molecules, which is the next step here. But if you notice here, in order to attach all of them around the center, it's going to take 2, 4, 6, 8, 10 electrons altogether, which means that this central atom is an exception. But that's okay because the method already told us that this is an exception. So we're going to acknowledge that the central atom by just attaching them all in the middle is an exception. And then we're just going to go ahead and we're going to add full outer shells to all of them. And that's by adding 6 to each one. And hopefully when we do this, when we get done, I'm just drawing 6 around each one, we can do the math. And that's not an extra one here. So there are, each one of these right here on the outside are 8. So 8 plus 8 plus 8 plus 8 plus 8. Pretty sure if I do 8 times 5, that's 40. So this right here is the correct structure. Now, what I suggest you do is tackle the problems that I have here at the end of the worksheet, just to do this to see if you can do them. And then in class, we'll be going over these again. Hopefully this has helped you. And if you have any questions, I'm always here in the morning, lunch, and after school, and I'll be available during your free time. The answer keys to the worksheets are on my desk, and you are welcome to come and take a look at them. Have a great day.